Welcome everyone to the first video of the series of videos for Calculus 1. We'll start Calculus 1 with the chapter limits, and the section that we are going to start with is the tangent and velocity problems. In this section, we'll learn how the idea of a limit is involved in solving the tangent and velocity problems. We'll also recognize a tangent to a curve at a point as the limit of secant lines, and also we'll identify instantaneous velocity as the limit of average velocity over a small time interval. Before we begin with that concept, I just want to spend a few minutes on why we study calculus. Um, So the first thing, calculus comes from Latin, which means small stone, or understanding something by looking at small pieces. It is also considered as the study of continuous change. Calculus has many applications in so many fields, including science, engineering, economics, and so many others. But today here, I'm going to talk about two foundational concepts or idea that led to the development of calculus. The first one is, for example, you are given this curve f of x, and then we are asked to find the slope of the graph at a particular point. Let's say this is this point here. Let's say this is A. So I'll write this point as a comma f of a. Now, if we have to find the slope at that point, with the math that we have learned so far, we really cannot do that, because in order to find the slope, we need 2 points. So to find the slope of a line, we need 2 points. And this is not a line, it's a curve. And we are trying to find a slope at a particular point. And another thing that is important to note here is on that curve, the slope changes at every point. It's not like a straight line where the slope is constant. So this cannot be done with the algebra or the ordinary math that we have learned so far. So this is one of the reason that we need calculus. So we can say the first reason is to find the slope of the graph at a given point, okay, of the graph at a point. Now, these basic concept or these idea will lead us to two major topics in calculus. So the first one is called limits, and that's what we are going to cover in this chapter. And the second major topic, the limit, will lead to another major topic that is called derivatives. And combining these two will make one branch of the calculus, which is called differential calculus. And then in this course, we'll probably spend around 75 to 80% of our time, or the content in this course is based on this first branch of calculus, which is differential calculus. So as a summary, this branch of calculus, what it does is it will take things and cut things into smaller pieces and then help us to study the change. So basically, we'll take something, we'll dig deep into smaller pieces, and then we'll study the change. So that's what the differential calculus does. Now, another reason to study calculus is, for example, we have the same curve here. Let's say this is f of x. And then what we want now is we are interested in finding the area of this region. So let's say this is A, and we have this line here. And let's say this is B, and then we have this line here. So now, for example, we are interested in finding the area under the curve, okay, and between the x-axis and those two lines. So this area, we are interested in finding this area. So now, when I say finding an area, you might think about the geometry, because we have so many formulas in geometry to find the area of any region. But usually those geometry formulas are for regular shape, okay? like rectangle or triangle or square or trapezoid. But here, this is not a regular shape that we see in the geometry. So this is any kind of region. So this is basically, to find this area, we cannot use some geometric formula, except in some exceptions we might have rectangle or triangle or square. We can do that. But in this case, for example, for any region, we don't have a nice formula in geometry to find the area. So what we do is we'll use calculus to find this area. So this is the second reason that we are learning calculus. So to find the area under the curve, let me just write under the curve, and we'll extend this later to between the curves, and when we move on to calculus 3, we'll extend this to a surface and so many other things. But let's just put that here now. Now this concept or this idea will lead us to another major topic in calculus, which is called integration. And then this branch of calculus is called integral calculus. So unlike differential calculus, what this one does is it will take small pieces. For even for this example here, we'll divide this into small pieces, small regions or small intervals. And then those small regions, they look like a rectangle. So we'll find area for each rectangle and we'll add them up. So that's the concept here. Okay, so what does integral calculus do is it will take small pieces and it will put things together. It will put those small pieces together and then find how much. The differential calculus will break things into smaller pieces and it will help us to study the change, whereas the integral calculus takes small things, puts them together, and tells us how much is something. Okay. So in this course, we'll again, I think it's like 20 to 25% of our course is on that topic, integral calculus. And when you move on to calculus 2, you'll continue with the integral calculus. So now we are going to study start the first chapter, the first section of calculus, and that is about tangent and velocity. So the first definition that we have here is the average velocity. So if any particle or a body or an object is moving along some curve, let's say the curve is y equals s of t. So the average velocity is given by this formula right here. So S of B minus S of A divided by B minus A. Now, let's put that in the graph. Okay, so let's say A is a point here, X value here, or T value, and then the corresponding point on the graph is A comma S of A. So let's say this graph is a graph of the function S of T. And then let's take another point, let's say here, B, and then the corresponding point is B comma S of B. Now, if you look at this formula, basically what we are doing here is we are taking S of B, the second coordinate or the y coordinate here, minus S of A, the y coordinate of the first point, divided by the x coordinate or t coordinate of the second point divided by the t coordinate of the first point or the x coordinate. So this is same as writing y2 minus y1 over x2 minus x1. And then this is very familiar to you. So basically what we're doing is we are finding the slope of a line here, and the line is the line connecting those 2 points, this line. So basically this formula here gives us the slope of that line, and this line has a special name which is called secant line. So from here we can say average velocity is same as the slope of the secant line connecting those 2 points. Okay. Now let's look at a problem here. So a projectile is launched from the ground level with a speed of 64 feet per second. The position of the projectile after t seconds is given by this function right here. And then we are asked to find the average velocity of the projectile between each pair of time. So now here, the first pair of time is t equals 1 second and t equals 4 seconds. This can also be written as the interval 1, 4. So now we know that the average velocity is given by s of b minus s of a divided by b minus a. Now here b is 4, a is 1. So what we need to do is we need to find s of 4 and then s of 1. So in order to find S of 4, we'll take this one and plug it in here for t. So negative 16 times 4 squared plus 128 times 4 gives us, so if we put this into the calculator, we will get 256. Now similarly, let's go ahead and find S of 1, which is negative 16 times 1 squared plus 128 times 1. And then when we put this into the calculator, we'll get 112. Now, the average velocity for this problem, the first one, A, is S of 4 minus S of 1 divided by 4 minus 1. And we know that S of 4 is 256 minus S of 1 is 112 divided by 4 minus 1 is 3, and then that gives us 144 over 3, which is equal to 48 feet per second. So that is the average velocity over the interval 1, 4. Now let's go ahead and do part B of this problem, where we are finding the average velocity over the interval 1, 3. So we already have S of 1, so we'll go ahead and find S of 3. We do the same thing, so negative 16 times 3 squared plus 128 times 3 equals, so if we put this into the calculator, we'll get 240. Now, the average velocity on that interval is given by S of 3 minus S of 1 divided by 3 minus 1, and S of 3 is 240 minus S of 1 is 112 divided by 3 minus 1 is 2. Now 240 minus 112 is 128 divided by 2. That gives us 64 feet per second. And that is the average velocity over the interval 1, 3. Now let's talk about another terminology here, which is instantaneous velocity. So now average velocity, for average velocity, we had an interval. So we are finding the average velocity over an interval. Now instantaneous velocity means is the velocity of the object, moving object, at a given time, at a particular time, x equals a. Okay. So now we have two formulas here and they are equivalent, and I'll just show you why they are equivalent. So what we are doing here is, let's say this graph represents the graph of the function s of t, and let's say this is a. Let's say here we have b, and this point here is a comma s of a, and this point here is b comma s of b. Okay, now if you look over here, this just looks like the formula for average velocity. Okay, and then the only difference here is we are saying instantaneous velocity equals is same as the average velocity, but we are taking b very close to a. That means this means b approaches a. or B is very, very close to A. The difference, the distance between A and B is very, very small. So when we do that, it still is an average velocity, but when we move that point very, very close to B, okay, then that gives us the instantaneous velocity at A. So what we are doing basically is here we are moving this point B, this t value be very close to A, or we are moving this point along the curve towards A, and we are bringing it very, very close to this point here, okay? And that gives us the instantaneous. That does not give us the exact, but it gives us the approximate value for the instantaneous velocity. That's what this one says. Now we have this formula, and I'm telling you that these two formulas are same. There's no difference between those two formulas. It's just the way that we are writing it differently. So this is how they are same. Okay, so here you see this h. So h is the distance between A and B. So this h. So for example, if we have A here, now if this distance is h, now instead of writing B, what we can write is we can write this B as A plus h. So for example, if you have a number 2 here and this is 3, the distance between 2 and 3 is 1. So instead of writing 3, we can write this as 2 plus 1, which is 3. So that's what we're doing here, okay? So instead of writing B, we are writing A plus h. And then that point here, the coordinate point up here, that becomes, instead of A, we have A plus h, comma, as of A plus h. So instead of writing B, we are replacing B with A plus h. Now, if you write that average velocity formula, that becomes S of B, but here is S of A plus h minus S of A divided by B minus A, means A plus h minus A. And that gives us S of A plus h minus S of A divided by h. So in this case, what we are saying is, in this formula, the second formula, we are saying B is very, very close to A. So instead of saying that, what we are saying in this formula, or this formula here, we are saying that h is very, very small. It's almost zero. It's approaching to zero. Means the distance between A and B is very, very small, or the value of h is very, very small. It's almost zero. It's not zero, but almost zero. So when we move that point, or when we move that B very, very close to A, such that the distance between them is really, really small, that average velocity, okay, that average velocity will give us the approximation for instantaneous velocity. So that's the idea that we are using here. Now let's interpret this in a little bit different way, okay? So that's how we got those two formulas. Now let's do the interpretation in a little bit different way. So remember, we were talking about the slope of the tangent line and the secant line. So we know that the average velocity is the slope of the secant line. So for example, if I draw this line here, okay, so this is the secant line. And then the average velocity S of B minus S of A divided by B minus A, this gives us the slope of this secant line. We saw that in the previous example. The average velocity gives us the slope of the secant line. Now what we are doing here is we are moving this point. Okay, so basically we are moving this point very, very close to this point right here, or we are moving this B very, very close to A, or we are making this distance between A and B approximately zero. So when we do that, as we move this, if we move this over here, now this is the secant line, okay? If I move that further here, I have another secant line. So if I keep doing that, and when my that second point is very, very close to the first point here, almost, they're almost identical, okay? So in that case, what happens is, so this line, the second line that we have, okay, approximately becomes the tangent line. So when that distance is very small, the average velocity approximates the instantaneous velocity, and in the similar fashion, the secant line approximates the tangent line. Or in another word, this instantaneous velocity is almost like the um, slope of the tangent line. So from here we can say the average velocity gives us the slope of the secant line, but the instantaneous velocity gives us the slope of the tangent line. So that's the idea that we're building up here. Okay. Now you might have, what's the difference between, you might have a question, what's the difference between average velocity and instantaneous velocity? So when I say average velocity, we are finding that velocity over an interval of time. Or when I say instantaneous velocity, we are finding the velocity at a given time, at a particular time. So when you're driving your car, the speed that you see on your odometer is the or the speedometer, sorry, in the speedometer is the instantaneous velocity or instantaneous speed. So it's the speed at an instant, okay, at particular time. Now let's look at a problem. So what we're doing here is, now we want to find the instantaneous velocity at 3. And what we're doing here is we are taking a point here that is 2, and we will find the average velocity on that interval 2 comma 3, and then we'll move closer to 3, and we'll take another number which is 2.9, and we'll find the average velocity between these two numbers. And then we keep that process, we keep moving closer and closer to 3, and we'll go very, very close to 3, and we'll find the average velocity. And when we do that, okay, so when we find the average velocity between those 2 points which are very, very close, that gives us the approximation for the instantaneous velocity at 3. So that's what we are doing here. Okay, so we'll take 2 comma 3, we'll take 2.9 comma 3, so this is 2.99. Okay, so 2.99 comma 3, then 2.999 comma 3. So that will give us an idea of what is the instantaneous velocity. We can make a conclusion from there. So let's go ahead and do this problem. So the first one, we are going to find the average velocity between 2 on the interval 2 comma 3. So what we need to do is we need to find the value of the function at 2 and 3. So we are going to find, so as of 2, okay, that is negative 16 times 2 squared plus 100 times 2. And then when we do that, so you can just put this into your calculator. Okay, so when we put that into the calculator, we'll get 136. Now similarly, let's go ahead and find s of 3. So negative 16 times 3 squared plus 100 times 3 equals, and that gives us 156. Now let's find the average velocity on the interval 2 comma 3. So the average velocity is s of 3 minus s of 2 divided by 3 minus 2, so which is, so s of 3 is 156 minus 136 divided by 1, and that gives us 20 feet per second. Okay, that means the average velocity on that interval is 20 feet per second. So similarly, we can find the average velocity for rest of the intervals that we have. So let's go ahead and find on the interval 2.9 and 3. So I'm not going to show you all the work. So I have already calculated s of 2.9, which is, so you can just plug it into the function and you can find, so s of 2.9 is, I got 155.44. And s of 3 is already here, so we'll use this one. Okay, so now the average velocity on that interval is s of 3, which is 156, minus s of 2.9, which is 155.44, divided by 3 minus 2.9. And then if you simplify this and put it into the calculator, you'll get 6 feet per second. So this is 6 feet per second. Now similarly, let's go ahead and find on the next interval, which is 2.99 comma 3. So this is 2.99. Okay, so we have to find s of 2.99. So when you plug it into the function and put it into your calculator, you'll get 155.44. 0.9584. Now the average velocity on that interval is 156 minus 155.9584 divided by 3 minus 2.99. And then when we simplify this, we'll get approximately 4.16 feet per second. So this is 4.16 feet per second. Now let's find the final one, which is in this interval 2.999. So let's go ahead and do that. Okay, so on the interval 2.999 comma 3. So again, we need to find s of 2.999. When we plug it into the function and then put it into the calculator, we'll get 155.995984. And then the average velocity equals s of 3, which is 156, minus 155.995984 divided by 3 minus 2.999. And then when we put this into the calculator, we'll get 4.016. So if you want, we can go farther and farther closer to 3, but with this, I think we'll be able to approximate the instantaneous velocity. Okay, so that's what we got for this one. So we started with 2 comma 3 and we got 20. When we move closer to 3, we got 6. Further closer, we got 4.16. Further closer, we get 4.016. It looks like now it's not going to go below 3. If we have to check, we can take more points and check that, but it looks like it's not going to go below 4. So I think this number is going to approximate or going to approach to 4. Okay, so now we'll just make a conclusion that the instantaneous velocity, okay, the instantaneous velocity at t equals 3 is 4 feet per second. Now here it doesn't, as I told you earlier, that this is not going to give us the exact instantaneous velocity. We just have to look at the number and just make an approximation. It looks like it's approaching to 4, so we say it's 4 feet per second. Okay, but later on, as we progress with this course, we'll be able to find a way to find the exact instantaneous velocity, and we'll take this example and then find exactly it's 4. Okay, but now at this point, we're just going to approximate in this way. Now that's the instantaneous velocity. Now our goal again is to find the slope at a point on the curve, on the graph, and then find the equation of the tangent line. So that's the next example. Okay, so here it says find the equation of the tangent line, this tangent to the curve here, to this curve at x equals 1. So what we are doing is at x equals 1, so I think it is somewhere here, x equals 1 somewhere here. Okay, so it should be down somewhere here. So we are trying to find the slope, sorry, the equation of the tangent line somewhere here. Okay, it's hard to draw, but somewhere here. Okay, so that's what we are trying to do. At x equals 1, we're trying to find the equation of the tangent line. Now, as we talked earlier, the slope of the tangent line is given by the instantaneous velocity. So now, in order to find the equation of a line, first thing, in order to find the equation of a line, what do we need? We need a point and a slope. So we need the slope and the point. So we are going to use the instantaneous velocity formula to find the slope of the tangent line. And then in order to find the point, we already have the x value. So we are given the x value. So we just need to find the y value in order to find the point where we are finding the tangent. Okay, so now as x equals 1, so what's the value of y? So we are going to substitute that over here, and then we can find y equals 1 cubed minus 9 times 1, and that is negative 8. So our point where we are finding the tangent line, or it's also called the point of tangency, that point is 1 comma negative 8. Now what we need next, we need this slope, and the slope of that tangent line is approximated by the instantaneous velocity. And we have that formula, which is s of a plus h minus s of a over h. Now here a means the x value, which is 1. So a equals 1. Now h is the distance between a and the other point. But remember, we say that in order to approximate the instantaneous velocity or the slope, we really need to take the other point very, very close to this point. So uh, closer that number, better value or the better approximation we are going to get. So you have to be really careful here. You are not going to take h equals 1 or 2 or 3. So that's not going to give you anything even closer to what you are trying to find. Okay, so you have to make that h value as small as possible. The smaller you make it, better result you'll get it. So what I'm going to do is I'm going to take h equals 0.0001. So I'm going to make it really small, okay? So if that is the case, then a plus h or the b value, so you really don't have to worry about this is same as saying b, okay? So the b is 1.0001. Now, we already have the value of the function at a, which is negative 8. Now what we need to do is we need to find the value of the function at this point. So we need to find, let's say y, let's not say s here because our function is y equals. So y of 1.0001, that equals 1.0001 cubed minus 9 times 1.0001. And then if we put this into the calculator, we are going to get negative 8.000599997. Okay. So now let's go ahead and use the instantaneous velocity formula to find the slope of the tangent line. So the slope of the tangent line is approximately equal to y of 1.0001 minus y of 1 divided by 1.0001 minus 1. Okay, and this is negative 8.000599997 minus y of 1 is negative 8 divided by, if we do the subtraction, we get 0.0001. Now when we simplify this, we are going to get, so I'm just going to write the final answer. We can put this into the calculator. We are going to get negative 5.999699, and it keeps going on, so I'll just stop here. So this looks like this is approximately equal to, with the confidence, we can say this is negative 6. So the slope of the tangent line equals negative 6. And then we have the point that we are finding the tangent line at, which is 1 comma negative 8. Now using this point and the slope, we are going to find the equation of the line, and which is the equation of the tangent line. Okay. Now in order to do that, you can either use y equals mx plus b, which is the slope-intercept form of the equation, or you can use the point slope form, which is y minus y1 equals m times x minus x1. I'll show you both, and then you can pick one way to do it, okay? So you don't have to do both. So the first one, let's go ahead and use y equals mx plus b. So when you're using this, y is the y value of the point, which is negative 8, equals m is the slope, which is negative 6, times x is 1 plus b. Now if you solve for b from here, you'll get b equals negative 2. That means the equation of the tangent line is y equals mx plus b, means minus 2. Now let's see the other way. If you are using this one, y minus y1 equals m times, so some of you might like to use this form of the equation, which is called point slope form or slope point form. So this one, you have to do y minus y1 means negative 8, so that becomes y plus 8 equals m is negative 6 times x minus x1 is 1. So that gives you y plus 8 equals negative 6x plus 6, And then if you solve for y, or if you subtract 8 on both sides, you get y equals negative 6x minus 2, which is same as what we got over here. So now you can either use the first one or second one, whichever you are comfortable finding the equation with. Okay. Now here, here's an example. I want you to try this problem on your own. So you can pause the video, try this problem, and then you can resume the video and check your work. So let's do this one now. So again, we are finding the equation of the tangent line at this point, okay, at this point to this curve. So now, in this case, we are already given the point. We have x and y values. So this is not an interval, okay? This is the point. So you have to be a little bit careful here. You might make a mistake, okay? So this is not a and b. It's not an interval. This is the point on the graph where you are finding the equation of tangent line. So this is x and y value. So now here a is 1. This x value is the value of a, and b is always something that you are going to choose, a number very close to a. Okay, so here we had the a value 2. Now let's take h equals 0 0.00, sorry, a is not 2, a is 1, my bad. A's value 0. We'll just take 0 0.001. Okay, that means a plus h is 1.0001. Okay, now in order to find the equation of the tangent line, we need the slope. We already have the point, so this is the point that we are going to use, and we'll find the slope. So slope of the tangent line is approximated by the instantaneous velocity. Okay, so this is approximately equals to s of, sorry, let me write y, not s, y of 1.0001 minus y of 1 divided by 1.0001 minus 1. And now we need to find y of 1 is 2. So if you do y of 1 equals 2 times 1 is squared, you are going to get 2. And then we need to find y of 1.0001, which is 2 times 1.0001 squared. And if we put this into the calculator, we are going to get 2.00040002. Okay, so this is 2.00040002 minus 2 divided by, when you subtract that, you get 0.0001. So this equals 0.00040002 divided by 0.0001, and then this is approximately equals to 4.0002, which means the slope of the tangent line should be 4. So it's approaching to 4. Now we have this slope, which is 4, and then we have the point, which is 1, 2, and then using this point and this slope, we are going to find the equation of the tangent line using y equals mx plus b. Okay, so y equals mx plus b. So y is 2 equals m is 4 times x is 1 plus b. Now if you solve for b from here, you get b equals negative 2. So that means the equation of the tangent line at 1, 2 is y equals mx, which is 4x, plus b, which is minus 2. So we'll just do this much for this video. In the next video, we'll see the definition of limit.